So IBM just pulled off something a lot of people in the chip world would honestly thought was still years away. They built a working chip at what they're calling the 0.7 nanometer node, 7 angstroms. And if that number means absolutely nothing to you right now, don't sweat it, because by the end of this video, you're gonna understand exactly why engineers are losing their minds over it, and why it might be one of the most important things to happen to computing this whole decade. Stick with me, because this one gets genuinely wild, and if you're into breakdowns where we actually dig into how this tech works instead of just parroting the headline, hit that subscribe button right now so that the next one lands in your feed. Trust me, you're gonna wanna see where this goes. Alright, let's get into it. On June 25th, 2026, IBM announced the world's first sub-1 nanometer chip technology, and the headline figure is almost hard to wrap your head around. They packed nearly 100 billion transistors onto a single chip about the size of your fingernail. That's roughly double the density of IBM's 2 nanometer chip, the one they showed off back in 2021. Double. In 4 years. Now, I want to be straight with you about the name because I think it matters. 0.7 nanometers is not the real width of anything on the chip. IBM said it themselves. Node names stopped describing an actual physical measurement years ago. These days, it's more of an industry label, a generation marker, part branding, really. So nobody is out here claiming they carved a little 0.7 nanometer wide into silicon. What they actually did is way cooler than a single number anyway. For about 60 years, the entire chip industry ran on one dead simple idea: shrink the transistor, make it smaller, cram more of them in, and get more speed. Burn less power, then rinse and repeat. That's basically Moore's law in one breath, and it worked beautifully for decades, which is a huge part of why the phone in your pocket embarrasses the supercomputers of the 1990s. But here's the wall. We're now working at a scale where the channel inside a single transistor is only about 15 silicon atoms across. 15. You cannot keep shrinking forever because eventually, well, you run out of atoms. Electrons start leaking where they're not supposed to go. Heat turns into a nightmare. The physics just stop cooperating. Everybody in the industry has watched this wall coming for years, and the question was always the same: what do we do when we can't go any smaller? IBM's answer is basically, fine. We'll stop going smaller. We'll go up. Now, this is the part that I love. The real breakthrough here is not the size at all, it's the architecture, and IBM calls it NanoStack. Instead of laying transistors on side by side on a flat surface the way we always have, NanoStack takes 2 complete transistors and stacks them vertically, one sitting directly on top of the other. One of them is an N-type, the other is a P-type. Those are the 2 flavors you need to build logic in the first place. IBM stacks them and staggers them in 3D, and here's the sneaky little clever bit. Because they live in separate layers now, engineers can use different materials for each one, tuning the top and bottom transistor independently, one for raw performance, one for power efficiency. That kind of flexibility is genuinely a big deal, and it is something you simply cannot do when everything is jammed onto one flat plane. Now, you might be thinking, okay, stacking, cool. Now, why is that even hard? Well, building a second transistor right on top of a finished one sounds simple until you look at how chips are actually made. Fabricating a transistor takes hundreds of steps, and a whole lot of them happen to be at brutally high temperatures. So, if you try to build your second transistor directly on top of the first one, all that heat basically cooks the device underneath it and destroys it. That's the trap that had this idea frozen for years. IBM's workaround is where it gets clever. Instead of building both transistors on the same wafer and frying the first one, they built them on 2 completely separate wafers, each one fully finished, and then they bond the 2 wafers together. And the way that bonding actually works is honestly kind of unbelievable. When you take two surfaces that are impossibly clean and atomically smooth and you bring them into contact, they start to stick together all on their own. They're held by van der Waals forces, which is that faint atomic attraction, the same basic effect that lets a gecko walk straight up a pane of glass. Then you heat the whole thing up and that gentle grip turns into permanent chemical bonds. The two separate wafers effectively become one solid piece. IBM does this with an ultra-thin dielectric layer wedged between the transistors, and they keep that bonding oxide under 30 nanometers thick so the two transistors sit as close together as possible without the layer wrecking the electrical behavior. But here's the scary part if you're the engineer running this. The process is completely unforgiving. The surfaces have to be perfectly clean, and one microscopic speck of dust, a single stray particle, and the whole bond fails. On top of that, the two wafers have to be aligned with nanometer precision because the transistors up top have to line up with the ones underneath, and you get exactly one shot. There's no peeling it apart to try again. When I read how tight these tolerances are, my honest first reaction was just, how does this even work even once? Okay, let's talk numbers because this is where it pays off. Compared to their 2 nanometer chip, IBM says NanoStack can deliver up to 50% more performance or up to 70% better energy efficiency. You pick which lever to pull. That is not a modest little bump. That's a full generational leap in one move. And there's one more stat that got the industry even more hyped, maybe more than the transistor count. SRAM. That's the fast memory that sits right next to the logic on the chip, and SRAM has been famously infuriatingly stubborn. It's basically stopped shrinking. For over 10 years, it's been the bottleneck everybody complained about and nobody could fix. IBM says NanoStack gets them 40% SRAM scaling, the first real gain in more than a decade. And if you follow this space, that single line is a huge deal on its own. But here's the thing that most people miss. This isn't really about making your laptop boot a couple of seconds faster. It's about AI. When you run a big AI model, a genuinely shocking amount of the energy doesn't get spent on actual math at all. It gets spent just shuttling data back and forth between the logic and the memory. That little trip, repeated billions upon billions of times, is where the power quietly drains away. It's like paying more for the delivery than you actually paid for the food. Stacking flips that. When you build vertically, you can physically put the memory much closer to the logic that's hungry for it. Shorter trip, less energy wasted, more work done per watt. And in a world where AI data centers are gulping electricity like it's going out of style, cutting that cost is enormous. This is exactly the kind of chip that an AI era is desperate for, and I think that it's a big reason IBM leans so hard on the AI angle. Quick side note too, this stacking idea isn't brand new. It already showed up in camera sensors, in high bandwidth memory, and in flash storage. What's genuinely new is that IBM pushed it inside the transistor itself. That's the leap nobody had pulled off before. Alright, real talk, because I don't want to oversell you. This is still a research demonstration. IBM has proven it works in the lab. They built a functional inverter, they validated it for bonding, they've got the receipts. But proving something in a lab and reliably cranking out millions of these chips are two completely different worlds. And that gap between them is where a lot of great ideas quietly die. And honestly, whether this one succeeds might depend less on IBM and more on the equipment makers. Wafer bonding at this precision needs incredibly specialized machines, and the companies that build them, names like EV Group and Tokyo Electron, are going to be central to whether NanoStack ever ships in real volume. IBM did this work at its Albany, New York research site with partners including Tokyo Electron, Lam Research, and Screen, and they're also bringing in one of ASML's high-NA EUV machines, the cutting-edge tool for printing patterns this insanely fine. IBM says they see a path to production in as little as 5 years, and 5 years in chip time is somehow both really soon and really far away. A lot has to go right between now and then. So, where do I actually land on all this? I think this is all genuinely exciting, and not in a shallow, hype way. For years, people have been writing the obituary for Moore's Law, insisting that we've slammed into a wall and computing progress is about to stall out for good. And what I love about NanoStack is that it quietly reframes the entire question. It stops asking how small can we make a transistor, and it starts asking how many can we stack up on top of each other. That's a completely different game, and there might be another full decade of runaway hiding in it, which is roughly what IBM is projecting. Is it a sure thing? No. Definitely not. The manufacturing could turn into a nightmare, and competitors like TSMC, Samsung, Intel, and iMac are all chasing stacked transistors on their own, so IBM is far from alone in this race. But being first to actually demonstrate a working sub-1 nanometer chip is a real milestone, and I'd bet the ideas here end up shaping what's inside our devices 10 years from now. If you got something out of this one, do me a quick favor and smash that like button, because it honestly helps the channel way more than you'd think. And hit subscribe if you want more deep dives like this one, because there's a ton more coming in the chip and AI world. Then drop a comment and tell me, are you optimistic about all this, or do you think that we're finally hitting the ceiling? I read every single comment. Thanks for hanging out, and I'll catch you in the next one.